Alright, this video is on effective nuclear charge. Effective nuclear charge is how much of the nuclear charge does the outer shell electrons see from the nucleus. It is important to understand this concept in order to explain periodic trends such as atomic radii, ionization energies, and electron affinities. So before we discuss this, just a little bit of background of where you should be. So at this point, you should have knowledge of atomic diagrams, orbital diagrams, and electron configurations. In fact, generally effective nuclear charge is discussed after doing electron configurations. So effective nuclear charge, let's look at an element such as carbon. So carbon has 6 protons in the nucleus. And you should be able to say that, yeah, I know carbon has 2 shells around the nucleus. And in the first shell, there are 2 electrons. And in the second shell, there are 4 electrons. And just a refresher, again, the 4 electrons in the outer shell, that's called valence shell. So we have 4 electrons in the valence shell. And that's easily determined by looking at the periodic table and noting that carbon is in group 14 or group 4A, and elements that are in group 14 or 4A have 4 electrons in their outer shell. So we also know at this point, when we did isotopic symbols, that the symbol to represent the nuclear charge is Z. So the nuclear charge is 6 positive. But we also know that these 6 protons, the full charge, does not get out to the outer shell of the atom. And the reason why is if we draw a picture of carbon and its electrons, if we draw a 3-dimensional scale plot here, we know the 1s looks like this. S has a spherical probability of where the electrons are 90% of the time. And so there's 2 electrons in there, and that represents these 2 electrons here. Then we draw the 2s, which is further from the nucleus. And again, spherical probability, so there's 2 electrons in here. And then we have the p orbitals that are dumbbell shaped, and there's one on the z-axis and the x-axis and the y-axis. And in these p orbitals, we have 1 electron in one p orbital and another electron in another p orbital. So the 1s electrons shield the nucleus from effectively getting that full 6 positive charge out to the outer shell electrons. So we have to come up with a mathematical equation to determine the effective nuclear charge, the actual charge that reaches the outer shell electrons, and that is Z effective. And Z effective is equal to the actual nuclear charge minus a shielding constant, sigma. Now sigma it's fairly complicated. You have to talk about the point charges, the positive charge of the nucleus, the negative charge of the electrons. You have to take into account electron-electron repulsions. You have to take into account the effectiveness of a s orbital versus a p orbital versus a d orbital in shielding the nucleus from the outer shell electrons. So for practical purposes of general college chemistry, we are going to approximate this. We're going to say that Z effective is equal to the actual charge, so for carbon it's 6 protons, minus the number of inner shell electrons or core electrons. So when we look at carbon here, the 4 electrons here in the valence shell, the outer shell, and the 2 electrons here are the inner shell. So we're going to say 6 protons minus 2, the inner shell electrons, and we get a Z effective of about 4 positive. Now, that is an approximation. It's not the greatest, but it is going to simplify the calculation, and it will allow us to predict trends on the periodic table. Now, the one thing we're not talking about here is that Z effective is also dependent upon the distance from the nucleus to the outer shell, and that's not going to be part of this calculation, but it needs to be part of your determination of Z effective, that the further the electron is from the nucleus, the less influence the nucleus has on those electrons. So if we look at something like silicon, so silicon's in the same group as carbon, and it has 14 protons in the nucleus, and it has 3 shells instead of 2 because we're in the third period, and there's 2 electrons in the first shell, 8 in the second, and 4 in the third. And so that's a total of 14 electrons to go with the 14 protons. And so Z effective for silicon, we would say, is 14 protons, the actual nuclear charge, 14 positive, minus the inner shell electrons, which is 10. How'd you get the 10? Because this is the inner shell. This is the outer shell. So both carbon and silicon have 4 electrons in the outer shell. They have similar chemical properties since they both have 4 electrons in the outer shell, or the valence shell. And the Z effective is 4 positive again. But just keep in mind, this 4 positive is actually less than this 4 positive. And why is that? Because we are further from the nucleus. We are further from the nucleus, and we have more electrons between the nucleus and the outer shell. So even though we come up with the same Z effective, just keep in mind that silicon is going to have a less effective nuclear charge than carbon, even at 4 positive. All right, so let's look at a couple other elements. Let's look at sodium. So sodium is in period 3. It has 11 protons. Oops. Can I go back? It has 11 protons. Still, it has 3 shells because it's in the third period on the periodic table. 2 in the first shell, 8 in the second, and 1 in the third. All right, so Z effective is equal to 11 minus 10. So Z effective is 1 positive. Now, some of you might have caught on by now that Z effective is going to be the same as the number of electrons in the outer shell for that element. And so, technically you wouldn't have to calculate this formally every time. Again, carbon and silicon being in group 14 have 4 valence electrons. Their Z effectives are 4 positive. Sodium being in group 1 has a Z effective of 1 positive. So what we know is that because the Z effective is less here than it is for silicon, we would expect sodium to be a larger atom than silicon. Since there's less effective nuclear charge getting out to the outer shell, those electrons are not going to be drawn to the center as strongly as a silicon's outer shell electrons. So that's where we're going with this, is based on Z effective, we are going to be able to predict trends on the periodic table. So based on this, we would expect the sodium atom to be larger than the silicon atom. And if we look at this, silicon is about 118 picometers, and sodium is 186 picometers. So what I find most students have trouble with is they say, well, generally when you add more of something, it gets larger. In this case, we're not just talking about mass. We are talking about the volume of the atom, and what determines the volume of the atom is the electrons. And so even though we've added 3 protons to make from sodium to silicon, remember those are in the nucleus, and the nucleus is very small, and again very, very small compared to the volume of the atom, which is determined by the electrons. So yes, even though we've added more protons and more electrons, the other point that we have to remember is that we've added more protons. The effective nuclear charge on those outer shell electrons has increased, and it does increase as we go across the periodic table, because if you stick with just period 3, you'll notice as we go across, we're adding more and more protons, and the core electrons or inner shell electrons is not changing. So therefore the Z effective increases, and that pulls the electrons closer to the nucleus. So that's where we'll stop this video presentation. The next video presentation we will talk about the trends on the periodic table, such as atomic radius, ionization energy, and electron affinity. Thank you.